The reality that we see around us isn't the only one. What if machine learning is not just data driven but physics informed? What does it truly mean to prepare a quantum state? And can we ever truly know what our reality is made up of? I'm Bhavidhir V. Bharadwaj. Welcome to episode 37 of Genesis of Tomorrow. The following is going to be a conversation about high energy theory, quantum computing, physics informed machine learning, multiverse, and many worlds interpretation with Dr. William Munizzi, a postdoctoral scholar at UCLA in quantum information and theoretical foundations in quantum computing. Furthermore, if you're interested in such deep science and deep tech conversations and are able to derive even the slightest bit of value from the show, please support us by clicking the subscribe button so that we can keep improving the quality of the episodes and keep on bringing such wonderful guests over for you. Also, folks, comment down below anything of intrigue and interest in the domain of science, technology, and more to you, which we can reflect on and maybe have some future episodes surrounding those particular matters. And now, without any further ado, let's get right into it. Enjoy and thank you. Okay, we're rolling now. So, Dr. Munizzi, welcome to the show. Before anything else, I think a very fundamental question is people talk about preparing quantum states, right? Going through the entire process of preparing qubits, aligning them, and just making the system work. What does it actually mean for somebody who's from a non-technical background to prepare a quantum state, and why is it such a fundamental step in the entire process?
Yeah, yeah, this is a very important question. So there are different ways to think about state preparation from a theoretical perspective as well as from a hardware perspective. So maybe I can give a little insight into both. Since I myself work on more of the theory side, when I think of state preparation, I think of constructing the appropriate unitaries, so the set of quantum gates, figuring out which quantum gates are needed to efficiently prepare the state in some abstract wave function or in some Hilbert space sense. Um, but more concrete and down to the hardware, the idea of preparing a quantum state is platform dependent. And so there are many types of quantum platforms out there, many companies that base their quantum computing devices on a particular model. And what that may mean for that particular model could be something with regards to taking a system of trapped atoms and moving these trapped atoms into a particular arrangement where they're correlated with one another in a way that they behave as an ensemble as this particular state that you're trying to simulate. It could mean something in the sense of superconducting quantum qubits, where you're instantiating some collection of these Josephson junctions, these superconducting devices, and coupling them through some electromagnetic coupling in a way that they mimic the type of state that you're interested. And so ultimately, it depends on the system itself and the type of quantum computing platform, but it always involves some sort of manipulation of a physical system, a sequence, a series of qubits, and getting them into some arrangement so that they behave as the theoretical state that you're trying to emulate.
To better prepare these said quantum states that we desire to achieve for them to perform the desired tasks that we want them to perform, how exactly can you make sure that instead of just working on an input and output basis, you can rather work at generating an entire distribution to maybe make them more efficient?
Are you asking how can you imagine manipulating a large system of
Yes,
quantum
yes,
devices at
scaling the
once?
entire process.
I see. Yeah, of course, right. So again, I'm not a hardware person, so my insights are going to be limited. But scaling is a major issue that we face in quantum computing, particularly for some of the reasons that you've already alluded to. Namely, it's very difficult to control a single quantum device because quantum devices are so noisy, so susceptible to error and decoherence. It is that much harder, oftentimes exponentially harder, depending on the platform, to simultaneously and accurately control a large ensemble of these quantum devices. That being said, there are various platforms and proposals which work better than others. I think what is one of the most promising are these neutral atom quantum computers, which have this nice built in scaling to them. They make use of these arrays of Rydberg atoms, and they allow you to essentially move the atoms to nearby locations within one another to control the correlations of interest. But the scaling for systems such as that, for platforms like neutral atom quantum computers or these silicon dot based quantum computers, are actually not terrible. They kind of follow the scaling of our current classical devices in a way, the way that you would imagine adding um, silicon dots to some like LED based television screen. But for certain systems that require superconducting temperatures, like superconducting quantum qubits, these things that have these massive dilution refrigerators required to even operate the device itself, the scaling is quite poor, and controlling them is a problem.
Quantum theory, as such, has been around for over a century. The mathematical formulations and ability to express it mathematically has also been around from since its inception. What is currently changing, or how is the demographic changing in terms of how we express our understanding of quantum mechanics mathematically? How is it changing today, if at all?
Yeah, I think that it's an interesting point that you make that the mathematics of quantum mechanics has in fact been established now since the 1920s, and so over 100 years, if not longer, in the cases of certain minimal aspects of quantum mechanics. But uh, as far as how the mathematics is changing, I think that our understanding of importance for utilizing quantum mechanics in quantum computing is changing a bit. And so what I mean by that is there are these studies of things such as like operator algebras. There's these studies of the mathematics that underlie different entanglement and the group theory that constrains the evolution under unitary action. These are types of these are areas of mathematics that have uh, existed in one form or another for many years, but perhaps are seeing a new time in the spotlight because of quantum computing. And so, while I think that the mathematics is largely the same, and the technology is what's been left to progress most in the last 100 years, I would say that there are specific areas of the mathematics which are becoming more prominent in the advent of quantum computing. And so, with the interest of applying quantum mechanics towards building the next revolution of technology, I think that we have some shift in which areas of quantum math are important or better to understand for our purposes. I'd say that would probably be my best guess right now.
What is the most relevant area of quantum mechanics or quantum computing by extension today?
I don't know that there's a single most relevant area. I wouldn't want to shortchange any one area in particular, as they all are important for forming this cohesive and successful effort. I would say that we are finding extreme importance in certain areas like unitary design, and basically the idea of how can we efficiently create and then ultimately perform the types of unitary actions that evolve a system, that simulate quantum dynamics or that prepare a state, as we had talked about a little bit ago. I would say that there are new adventures into um, maybe old topics such as superconductivity, as well as high precision lasing and ideas for controlling quantum systems. So any of the foundational theory that underlies how to control and accurately manipulate quantum systems is something that is of paramount importance right now, something that a lot of people are focusing on. I myself am very interested in the mathematics of entanglement and certain properties of quantum systems. So, these ideas of entanglement and magic and complexity, and how these particular quantities can evolve under the types of unitary actions or non-unitary actions that evolve a quantum system. And so I would say that something among these particular topics are all finding a large resurgence of activity.
Talking about entanglement a little bit more, uh, people generally have an idea of what entanglement is in terms of the definition aspect of it. Superposition, entanglement.
Mm.
These are the entry points that you get to know about when you get into the field. But from a theoretical perspective, how exactly are you entangling two qubits? Like, how are you exactly
Mhm.
doing that?
Right. So I think that I actually think we maybe don't fully understand what entanglement is, but we have an intuition for how it behaves. And so what we imagine is that we have some relation between entangled objects. And so let's call them particles at this point. And this relation exists even in the absence of correlation. So basically, if I can take a system and I can rule out all types of correlation, whether that be electromagnetic field interaction or whether that be some sort of strong field interaction, whatever it may be, what I'm left with is something that is still a fundamental connection between the objects, but it is not something I can attribute to some term in the Hamiltonian, for example. Now, as for how do we actually generate this entanglement, there are different ways to do it, but ultimately the idea is that we're beginning with some single quantum system and we're breaking that system up into pieces. And so, a very common example is that you can imagine taking some um, pair of electrons that are produced in a zero angular momentum state at somewhere in the universe, and we have the ability to say separate these two in such a way that one of them is going to have perhaps a spin up value, and one of them is going to have a spin down value, and this value of its intrinsic spin is fixed. This is something where essentially the two particles are entangled in the sense that we are not allowing them to interact through any classical physical means, but we know that if we were to flip the spin of one, that there would be some quantum foundational preserving operation like entanglement, which would flip the spin of the other one to accommodate this. Um, and I would say ultimately in the lab, it comes down to the idea of generating these particles in an entangled state. Or rather, what we do is we generate this system of objects in some state, which then when we separate them, they share this entanglement with each other. But I don't know necessarily of a means of taking two things. I mean, theoretically, I can envision how we might perform certain quantum computational operations which do this. Um, yeah, perhaps I could say a little bit more on that. So one thing you could also think about is the idea of superposition. Right? When we have superposition, we're imagining that there's some uncertainty in the wave function of a particle. So I have an object, it exists in some superposition, even though I don't see it in the superposition. When I go to make a measurement, I immediately project the object into one of the measurement basis states, and I can observe that. But if I were to somehow be able to transmit that uncertainty, that superposition, across to another particle, this is something that can be done, for example, with an entangling gate in quantum computing, like the controlled NOT gate or the controlled C gate. Um, if I perform this operation, what is essentially happening is I'm taking a particle that's in a superposition, and then I'm asking my device to essentially say, if this particle has a particular value, then perform this operation on my second particle. And if that value itself is uncertain, then the uncertainty is going to transmit to the second particle. And that's one form of entanglement that we come across most often in quantum computing. So I would say that's one direct way that you could imagine creating an entangled pair in a quantum system.
What was your first brush with a concept or a particular matter that was, in a sense, truly quantum, wherein you could not really decipher a reasoning to it through classical means? Like that first push towards the entire field of quantum domain where you were like, okay, right, this is something very interesting that I would want to go down the rabbit hole of?
Hmm. I would have to say that my initial one of my initial stimuli for being interested in quantum mechanics and sort of the strange foundational quantum behaviors that exist was probably Einstein's collection of writings on the spooky action at a distance, essentially like an admission of not understanding how quantum systems behave, particularly when it comes to things like non classical correlations, such as entanglement. Um, I would say that some of the original ER equals EPR papers and these idea of particles which themselves can have correlations that, well, I shouldn't refer to them as correlations, but they could have some sort of entanglement that spans the distance of the universe. And in a particular vision, you could imagine them um, uh, almost acting as if they have some faster than light communication between the two, even though we know that's not the case. But at naive observation, it almost appears that way and is enough to confuse some of the greatest physics minds at the time. I think that these types of ideas I found very fascinating. I also found very fascinating the notion of spin. This is something, again, that we don't fully understand. We know that all fundamental particles possess this property which we call spin, but we don't know where it comes from and we don't fully understand how to describe it. We understand the mathematics of it, but we don't understand physically where it's arising, and yet it still physically influences fundamental interactions, such as interactions with a magnetic field, being completely determined by the spin angular momentum of a fundamental particle. I think that these things are very strange and they lend themselves to very natural mysteries worth looking into. So I would say, along those lines, the typical introductory concepts you encounter when you first learn about quantum mechanics.
For me, among other things, it was how do you how you are able to apply these things, these different phenomena towards the domain of computation. And coming on to that a little, how exactly does high energy physics and quantum mechanics it applies towards or maybe translates into computation aspect of it? Quantum information and everything, the entire diaspora there.
Hmm. I think there's a lot of relations between physics and particularly high energy physics and quantum information, quantum computation. There's a couple different topics that we could discuss in depth. I would say that we have hopes that. So one thing I should say is that one of the reasons that high energy physics is so difficult lies in the high energy side of it. When we have systems that are operating at high energy scales, we find that the quantum effects are harder to pin down. And so, in the case of something that is a low temperature phenomena like superconductivity, we know that we are able to effectively uh, cool the system down so the thermal effects can effectively be separated from the quantum effects. But in the case of these high temperature interactions where we have large energy scales, the the spectrum of energies becomes almost continuous in a quantum mechanical sense, and also we have this just extreme number of correlations that are existing. We could imagine things like a strong coupling limit of some field theory. We could imagine things like the types of interactions that occur inside of some nucleon, some sort of strong nuclear force interaction. These are the types of questions that are, in principle, difficult to answer. Um, and I think that there are hopes brought upon by various new efforts, fairly new, I'll say, uh, efforts that combine quantum information and high energy physics. I myself am very partial to ideas stemming from holography. So this is one theory of most famous realization would be ADS-CFT, which is anti-de Sitter conformal field theory, and this is a mathematical duality that describes a particular spacetime with a weak coupling, meaning that it's virtually classical gravity. It's semi-classical gravity where quantum corrections come in at higher orders, and its relation to strongly coupled field theories of a particular type. And I think that the types of influences that ADS-CFT could perhaps give to quantum computing are numerous. And I also think, on the other end, the hope of using quantum computing to simulate something like ADS-CFT or to simulate high energy physical interactions are definite goals of the field right now. So the two are playing in complement with one another, with the hope that there's some overall benefit to be gained from both parties.
Where exactly do we utilize machine learning in the entire area of physics and that regard?
Hmm.
Like, surely people do know
Yeah.
it's significant, but like, why?
Why is machine learning significantly utilized throughout physics?
Yes.
Yeah, I think that I still think that we're finding utility for machine learning well beyond what we ever imagined. The field itself is rapidly developing. I think that part of the reason we find it so useful is that it gives us an opportunity to perform numerics at a rate that might have otherwise been very difficult to perform. I'm not an expert in machine learning. I do utilize machine learning in certain aspects of my work. In particular, I'm interested in using machine learning to do certain tasks that I otherwise would be doing myself naively. And so the idea of, if I have to search some enormous phase space for some reason, I'm trying to identify a particular um, maybe I'm trying to identify a particular state in the Hilbert space, or I'm trying to identify a characterization of states with certain properties. I could sit there and I could attempt to think very deeply about it and understand why and where I should look for these states. But I could also imagine training a reinforcement agent, for example, to find its way through the space and then return the data to me, which I could then hope to interpret and make a more clever approach for this process. Um, I also think that there are a lot of these problems, particularly in high energy physics, that do have a high numerical aspect to them, so that they rely very heavily on being able to perform numerics. And I think that machine learning models are very good at that and very good at optimizing numerics. And this is something where I think they find great utility in modern physics.
One other aspect that I'd like to inquire from you about is of how do this current variety of the quantum chips that have come up in the past year or so in the market from all these big tech companies, how do they work, and what are, I mean, naively putting it, people, it can be said that maybe Google's Willow quantum chip, it is basically parallel computing on steroids. And to maybe draw that the workings of how they work and everything, talk about topological computing in Murana, Microsoft's Murana one. What are the different approaches that these different companies have taken to build their quantum chips, and what just makes one more efficient or better or not in some regards or other than the other?
Yeah. Um, so I would say that beginning with sort of some of the first ideas of successful quantum chips, like coming out of IBM, for example, is um, uh, IBM and others, is trapped ions or these superconducting qubits. I think the idea is that if you can take some device and lower it to a sufficient temperature, then again, you get this nice decoupling of thermal degrees of freedom and quantum degrees of freedom, and you could hope to manipulate just the quantum degrees of freedom. And this may come, and again, platform dependent, this may come by applying a particular voltage, which places the the system in a certain arrangement, or this may come from some magnetic field which orients your system in a particular arrangement, and then manipulations follow from there that you're performing quantum gates and quantum operations by essentially classical processes that are just manipulating the orientation, the state itself. And then the quantum connections between these, whether it be through entanglement or whether these be through some other interaction, are then governing how the chips talk to each other. But some more ambitious designs, the idea of like these Majorana topological quantum computers, the process is definitely it's distinct. The main difference being now we're not considering necessarily having, let's say, a single atom which has an associated set of parameters like spin and angular momentum, and we're trying to manipulate that as some sort of vector in space. But instead, we're considering now instantiating in a material some long range correlation, which is going to act as our qubit. And so typically these are referred to as anyons. The reason they're called anyons is because they exist as these quasi-particle excitations in the material, which can take any spin value. And so we're not thinking of them as bosons or fermions, but as something in between, which we can tune that spin parameter. And these anyons are, in principle, these extended objects, which reach, when I talk about far distances here, of course, we're still talking about microscopic devices, but the idea is that the interactions are long range through the material, which leaves them very robust to local perturbation. The idea is that if I disturb the system at some region, I can rely on the fact that the interactions that are governing the device are spanning a much further distance, that there's actually an additional layer of what's called topological protection in the system. And that's one reason that these are considered to have a potential advantage over other models. And so what I'm saying is that the topological quantum computing is a very promising approach for quantum computers because it essentially eliminates a lot of the error correction that's needed and the error mitigation that's needed for other devices, because you have this inherent topological protection. Now, that doesn't come without a cost. The manipulation of these anyons is in principle a tricky process. People refer to the process of braiding, which is the idea if I have these extended objects and I need to essentially wrap them around each other in one way or another to correspond to some sort of quantum gate that I'm performing. And how we braid these Majoranas, how we braid these anyons is still an open question. We have proposals for how to do them, but to actually perform these operations on a real processor, a real quantum device, is tricky. So these platforms are different. Some promise advantages over others by way of the simplicity of implementing this, whether it just be manipulation of magnetic fields to implement certain quantum operations, and others promise perhaps advantages in error correction, and the error not having as large susceptibility to error also correlates to the scaling capacity, because when we scale up these systems, the error only gets worse. So that's another reason why people are very excited about topological quantum computing, for example.
Why has there been this immediate boom in quantum chips? Like, are we moving towards, have we reached that point where we are maybe looking in a few years, 3, 4, 5 years, towards widespread implementation of quantum technology, access to quantum technology?
Well, the short answer is almost certainly not, for several reasons. I don't think that we have, there is really no intention to have, or by many, to have widespread implementation of quantum technologies. So basically, I would not hold your breath waiting for a quantum iPhone. There is no reason why we would expect a quantum device to perform better than classical computers when it comes to microprocessing for cellular services or watching videos or listening to podcasts. Our classical devices do an excellent job of that, and the overhead needed to perform the same type of process on a quantum computer just likely would not be be useful, at least not in the relative future. Quantum devices are designed to perform a very specific purpose. Many of these purposes, which lie outside what we believe to lie outside the computational capacity of classical computers entirely. And so, one of the things that you may have heard of, is particularly with the release of the Google Willow chip, is this idea of random circuit sampling. This is a way of this is something which is inherently we understand that quantum computers are good at this process, and classical computers are not. And so when there are claims made that the best classical computers would take 10 to the septillion years to perform a similar calculation. These are, in principle, accurate comments, but it also alludes to this idea that the quantum computers are designed to do this sort of task. Something that's a little bit more perhaps digestible is the idea of simulating interactions in nature that have, in principle, many degrees of freedom. So imagine I wanted to take some atom that's larger than hydrogen. So I want to take like two carbon atoms and I want to actually simulate the real interaction, considering all degrees of freedom, of two carbon atoms. This is something we believe to be well beyond the scope of abilities for a classical computer. Um, there's just too many things, there's too many variables floating around, and to map each of these degrees of freedom to some binary operation, some bit string on a classical computer, requires an exponential overhead that quickly becomes intractable for problems of even a moderate size. However, if instead we could imagine performing these calculations where the chips, or more of the bits themselves that comprise the chips, are actually the elements we want to see interact, then the problem almost becomes trivial in the sense that we're just taking the atoms themselves and we're allowing them to interact, and we're just reading off the data we get from the system. If we can do that effectively, then the hope is that this is something a quantum computer will allow us to simulate, and do so in a way that we would not hope to have with a classical computer. And so, again, the biggest takeaway is that the problems that quantum computers are actively being designed for are very specific, and they are far, in many ways, they are typically far beyond the scope of what most people would seek computational resources for. You wouldn't look to have a quantum computer in your pocket anytime soon, and it probably wouldn't even be good for the purposes you'd like.
While while the Willow chip was being introduced, there was also a ton lot of fiasco around it proving the existence of multiverse. Shedding some light
Mhm.
over it, I did naively put it in a way like parallel computing on steroids. But maybe talking about it, the idea of many worlds and trying to facilitate it, trying to direct it towards the area of computing, how exactly do we approach at maybe trying to understand the entire notion a little bit of?
Well, with the many worlds interpretation, I should state that this definitely has existed for many years before um, this active research, most active research into quantum computing. So I believe this was initially put forth by Hugh Everett, and perhaps several others. Some early foundational researchers in quantum computing, David Deutsch being one, are large proponents of this many worlds interpretation. Some people prefer to call it a theory. I'm just going to refer to it as an interpretation. But the idea is that yeah, this is meant to be an understanding of reality. It's not something that I personally foresee impacting how we proceed with building quantum devices and implementing quantum computing, but it might enable an explanation for why we see the types of speedups that we do in quantum computers. But again, this all relies um, on the correctness of the theory itself. Um, I have not given a ton of thought to many worlds interpretation myself. Um, I surely find it interesting, but I think that it's just one of those ideas that quantum computing has upwards of 20, if not more, viable interpretations. And and all of them agree, at least in the sense of how we perform the basic calculations that we do when we mess around with quantum devices and when we build quantum devices. And so I don't foresee them impacting perhaps the efficacy of quantum computers, but we could hope to have a deeper understanding of nature that emerges after witnessing the success of quantum devices, perhaps contingent upon the viability of a theory such as many worlds. The claim from Google follows more from the comment I had made earlier, where if you have some process which you know must be performed in our universe and would take a classical computer longer than the age of the universe by many orders of magnitude to perform, can you infer something about where, and I should put where in air quotes, where in a spatial temporal sense the calculation is taking place? And the claim was that perhaps it is taking place in parallel across many universes. But again, I think this is a creative interpretation. I don't know how strongly I would subscribe to some of the beliefs, but I find it certainly interesting. And at the very least, it shows that we're pushing on the foundations of our understanding of nature at the most fundamental level, which is a fascinating thing to be occurring in our lifetime.
Another very interesting idea is that of conformal bootstrap and just non-perturbative quantum theories. Why is it so powerful, and what does it actually go on to reveal about quantum systems?
Yeah, this is shifting gears a little bit, kind of addressing some of the related high energy topics that we discussed earlier. But to give a general overview, first, when we talk about the conformal bootstrap, we're talking about a program that's useful for calculating data for conformal field theories. So, just a background, the idea of conformal field theories are a class of quantum field theories which are conformally invariant, which means that they're left unchanged up to some set of transformations on your spacetime. Namely, they are left unchanged under conformal transformations on your spacetime, which include the notion of scale invariance. So, zooming in and zooming out on your system will not change the physics of your field theory, as well as this particular mathematical type of transformation called special conformal transformations. And so you can write down the mathematics of these transformations and how they would manipulate a spacetime. And the idea is that there are classes of field theories which are unchanged under the action of these transformations. Um, these conformal field theories pop up everywhere in nature. They're not new. For example, the Ising model, where we imagine some collection of spins, so some collection of little arrows that represent little spin vectors, and they're allowed to speak to correlate with one another. It turns out in particular limits that have to do with the interatomic spacing as well as the correlation length, so how far of a distance these objects can talk to each other. For certain limits, this system admits conformal invariance. And then on the more abstract end, with quantum gravity, as I had mentioned earlier, we have our most successful theory of quantum gravity, namely ADS-CFT, and conformal field theories. They comprise one portion of that. They comprise the quantum portion, essentially, the quantum field theories that are strongly correlated, which map to this classical gravity picture. So that's kind of an introduction to conformal field theories. But you asked specifically about the bootstrap. So the bootstrap approach, typically when you go to evaluate a quantum field theory, you imagine writing down the Lagrangian and you attempt to understand the dynamics that are captured by this Lagrangian. But this can be difficult in generality. I mean, even for fairly simple yet useful systems, this can be a difficult process. And so the bootstrap approach completely throws out the notion of studying the Lagrangian and instead focuses on the symmetries of the system. So, for example, conformal symmetry, this conformal invariance that I mentioned, puts a lot of constraints on various objects in your field theory. One example is something that's like the operator spectrum is an example of this. So the spectrum of operators in your theory are constrained by conformal invariance. Another one is the operator product expansion. And so it turns out that these, when we consider operators that act locally, and so we want to imagine, typically, if we want to evolve this system, we imagine computing some correlation function, so an expectation value of a product of operators. Uh, when the product of these operators, when these operators are localized near one another, in the Bootstrap program, we can actually write down what's called an operator product expansion. So we can actually write down the product of operators as a sum over operators acting at a single point. And this weighted sum, it turns out, has a lot of fixed points. So the values of these coefficients are fixed or are severely constrained by conformal invariance. And so it makes this sum very easy to write down, and it strictly constrains the values that these weights can take. And by doing so, this allows us to probe beyond the capabilities of some perturbative approach, like a Feynman diagram. So Feynman diagrams are performing perturbative quantum field theory. This bootstrap approach allows us to essentially consider everything all at once in the field theory, all the operators, and their relations to one another, their products, and do so in a way that we can compute exactly in some systems, which is almost hopeless for general quantum field theories, and do so in a way that's analytically tractable because of the constraints placed by conformal invariance. I'm happy to talk more about some of these ideas if you'd like, but yeah, maybe you had another question about that.
Uh, Directed towards the area of quantum information, uh, can the bootstrap formalism, and if yes, then how can it help help us at building better quantum information structures?
Yeah, that's a great question. So maybe we can ask like what can we hope the right. So first, let me say, what are some of the ways that we may hope the bootstrap provides us with insights in the type of high energy physics questions we're interested in? One of them, I would say, and I think one of the most intriguing, if not the most intriguing objects in all of physics, are black holes. Um, so we know that black holes are themselves the some of the most violent gravitational objects that we can ever conjure up within general relativity, in the sense that we're making these extreme deformations to space-time that generate singularities or extreme or even infinite curvature. Um, we have these. We also know that they're quantum mechanical objects. This is a very famous result that stems back to Bekenstein and Hawking, showing that these are not only thermodynamic objects, but that they actually have some quantum behavior as well. That we can ascribe to them this idea of essentially this is our best toy for representing a quantum gravity object. And so maybe there's one hope that calculations in the bootstrap, which are able to probe things like high energy spectra, so the behavior of conformal field theories in the high energy limit, or the operators that are most meaningful in some high energy approximation. Um, there is some hope that perhaps these will yield insights into black hole microstates. So essentially, we know that there is a relation between these two objects, namely these black hole microstates and the particular properties of a conformal field theory, which are widely studied in ADS-CFT. There is some hope that perhaps by performing better and better calculations on the CFT side, we'd be able to get a little more insight into the structure of black hole quantum thermodynamics, for example. Now, how does that help us in quantum information theory? Well, inherently, the idea of black hole thermodynamics is tied with quantum information. These objects, they lead to these interesting. Uh, Typically, we call them paradoxes at first, and then we attempt to resolve them. But the most famous would be like the black hole information paradox, which relies specifically on both the thermodynamics of black holes and how it relates to the quantum information in our universe. I think that there is perhaps some hope if we wanted to model quantum black holes on a, or excuse me, if we want to model or simulate black holes on a quantum computer, there might be some hope that understanding more about CFTs and doing so via the Bootstrap, which is one of our best protocols for understanding conformal field theories, might be able to elicit a better way to design ultimate algorithms and simulations of black holes on a quantum computer. I could only hope that something like that happens to be true one day. I think we're many years off from that, but this is sort of a pie in the sky dream that, yeah, perhaps some better understanding of CFTs will actually allow us to simulate black holes better by understanding the quantum information and how it propagates through something like a quantum computer.
Uh, that really clicked a different question in me. But we were talking about entanglement a little while back. How exactly do these different and various quantum approaches that we have deciphered over the years impact our understanding of space time and the temporal dynamics of the said, maybe transfer of information, maybe relation between two different entities that we have established are quantum in nature, and a zillion other parameters and things.
Mm-hmm. No, that's a great question, and that's one of these very important, essentially like interpretation of reality questions. So there's a large school of individuals that believe that um, space time itself is not fundamental, but instead information is fundamental. And so the idea that if I have some amount of information, content in at a region of space, it essentially constrains the type of space times that I can have. And so essentially, this is the idea that, there's some blueprint, if you will, for the universe. There's some blueprint for space-time itself, which is constrained by the information content and the characterization of the information that is stored locally in some area of space. I'm sure I'm paraphrasing a little bit too much. I'm not someone. I'm not an active researcher in that area, but I think that this is a fascinating uh, pedagogical question to ask. Like, essentially, what is most foundational? Is it the objects that we are readily interacting with in our space time, or is it something that's a little bit more abstract? That there's like some set of data that underlies the space times that we see. In ADS CFT, we play around with these toy models a lot. We talk about things like space-time reconstruction, which is basically the idea that if I have some information content in my bulk spacetime, it's going to actively constrain the types of spacetimes I can build. And this is something that we're very used to. But with ADS CFT, we have to be careful because that's not necessarily our universe. That's not, we don't live in an anti de Sitter universe. And so the mapping from this mathematical model to our universe is subtle. It's something that needs to be done carefully if it can be done at all. Um, but I still think that the question remains interesting. Now, um, I'm sorry, what was the second part of your question?
In general, how do they define space-time, and secondly, the temporal dynamics between all these different approaches that we take to quantum understanding?
Sure. Um, Yeah, so I mean, in general, we typically just think of space-time as a set of coordinates uh, that incorporates both a spatial element as well as some temporal element. The temporal element is almost on equal footing as the spatial element in the sense that we believe that you can move at least in one direction in time just as freely as you can move in all directions of space. And then, of course, we have these various constraints that we expect to be true from our observations of the universe, that we can't go backwards in time, such as the presence of or the non-existence of what are called closed time-like curves. Um, and this is, of course, to avoid certain what would otherwise be paradoxical observations in physics. But yeah, the idea is that now how could these possibly be constrained by quantum information? Well, if there was some underlying structure that was governing how these geometries came to be. So if there were some, again, in the case of ADS-CFT, which is our best model that we have for quantum gravity, this happens to be the case. So basically, there's some information theory on the boundary CFT, on the quantum side of the quantum gravity, which constrains the types of geometries that can be built on the gravity side. Not only does it constrain the types of geometries that can be built, but it constrains the evolution of these geometries in time. And so basically, if you have some theory of quantum gravity and you have some blueprint for space time, which is constrained by properties of quantum information, then you could hope that the constraints and the evolution of that quantum information, that perhaps this quantum information needs to evolve unitarily, like the entire universe itself needs to evolve in some unitary way, that this could constrain the types of geometries which are accessible at certain instants in time. I think that this would be the way in which we might hope that quantum information and space-time kind of give rise to one another in some sense. But otherwise, yeah, I'm just speculating at this point.
Talking about the physical constraints a little, when we apply them to the quantum algorithms that we are developing, and maybe you can talk about quantum optimal control and dynamic decoupling, all those different matters while you're talking about this. But how exactly are we manipulating our the quantum systems that we are in the process of building through all these different physical constraints that we are faced with in the real world? But like, we know if we do not specifically define them in the right way, everything and anything will be possible in the simulation aspect of it. So like, how are we accurately applying these real physical constraints to our algorithms and
Hmm.
computational methods?
Well, you brought up a very interesting point with dynamical decoupling and optimal control. This is an example of how we might hope to implement what is otherwise a theoretical idea, like the action of a quantum gate, where we might hope to reliably perform this process on a real device, on a real system, an ensemble of quantum objects. Um, I would say that the most well understood example, okay, to understand first the notion of dynamical decoupling, at least in the way that I'm most familiar with, we imagine that we have a Hamiltonian which describes the interactions of your quantum system. And the idea is, what is reliability in this sense? Reliability is the ability to perform something as desired and with minimal noise. And here, noise can mean anything from actual noise in your system, like thermal noise or some sort of quantum decoherence, but noise could also refer to an inability, like a lack of precision in the operations you're trying to perform. One of the most or the most studied and well understood uh, dynamical decoupling schemes is what's known as a spin echo or a Hahn echo. This is developed for nuclear magnetic resonance systems. So the type of technology that underlies MRIs, for example, we imagine that we have a system of nuclear spins, for example, which point in some direction as set by an external magnetic field. And as these are pointing in a particular direction, we're going to hit this system with a perpendicular magnetic field, which is going to tip them over. As these spins tip over, they're going to begin to precess about the initial external magnetic field. And the precession frequency is determined by how far they are tipped over. And so one of the things that you realize right away is that if spins are tipped at different angles, for example, their precession frequencies are going to differ. And if their precession frequencies are differing, then the readout that you're going to get from your system is going to depend on how accurately you can tip these spins over. But one of the genius revolutions from Otto Hahn with the spin echo protocol was that what you could instead imagine doing is tipping these spins over and allowing them to evolve for, let's say, half the time that you want to run your experiment. And then you can perform a 180-degree pulse to flip them down and allow them to spin now from some other. So basically, you tip them over, you allow them to process for about half the time, and then you flip them another 180 degrees and you allow them to process for the remainder of the time. What this will do is it will take the spins that we're processing faster up top and it will move them so that in their new orientation, they're now processing slower. And so the difference between the spins, which is the source of noise in this case, is actually going to go to zero over the full evolution of your system. This is the simplest form of dynamical decoupling and is extremely effective when performing anything related to nuclear magnetic resonance. And what you can see is that you're not relying on any improvement in the technology. What you're actually doing is you're manipulating terms in the Hamiltonian to cancel out. So essentially, you're relying on the ability to implement external magnetic fields to cancel out any sort of error terms that could arise in your Hamiltonian. Um, we have since progressed this field tremendously. There are many different dynamical decoupling schemes that are more useful for systems that have not only some spin orbit coupling, but spin spin coupling, or many different ways that the particles interact with one another that we may hope to cancel out or to amplify signals that are of interest. Um, but the idea is still the same: is that one way to reliably perform quantum manipulation is to cleverly design these schemes that at the fundamental level, at that level of the Hamiltonian, are amplifying the signal that we want, the operation that we want, and are minimizing any sort of erroneous operations that could arise. Um, a brief comment on optimal control. Optimal control is very similar. What you're doing is you're manipulating the system and you're constantly getting a real time readout of what's occurring. And so you're perhaps performing some sequence of magnetic field pulses, which is taking your atom to various orientations. And what you're doing is you're using various measurement readouts that you have, keeping your pulse, keeping your finger on the pulse of the system, and then using the information that you get from that to direct the next sequence of pulses. And so essentially, if you find that you've over rotated your qubit by some amount, you have some way of interpreting that, and then you can correct the next operation to account for that. And so this is sort of a real-time feedback that you have on your system. And then there's various optimization algorithms that you perform on this process to actually optimize from a functional level the sequence of operations that you're performing. And these two, dynamical decoupling and optimal control, often go hand in hand as they're both extremely useful for implementing any type of manipulation of a quantum system. And I would say when you're going to perform algorithms, which ultimately rely on, if you're someone like me, you have the luxury of just building algorithms as unitary operators, and you just study the group theory, and that's completely robust to any sort of notion of error. But if you're somebody that an experimentalist that needs to actually work on these and implement them on the hardware, these are some of the ways that you may hope to implement the types of quantum gates in such a clever way as that you can get the overall unitary that you're hoping to design, or the algorithm or whatever it may be. Yeah, this is it's an extremely important part of quantum computing, one of the most important parts.
I think the discussion can be continued in much more depth and umpteen different directions that we can go from here. But for the
Mhm.
paucity of time, I'll move on to the final segment of the show. There's this one particular question that I like to ask everybody who's over towards the end of the discussion to give a sweet little conclusion, which is, Dr. William Munizzi, what would be your word to humanity at large?
I think that I would say it would be very nice to see people prioritize perhaps understanding of the world around us over perhaps differences in opinion or politics. I would like to see a strong concerted effort towards science and understanding nature. I think the ability to perform science is one of the greatest joys that we have in this life. Of course, I'm heavily biased on that opinion, but I genuinely believe the ability of the human mind to even comprehend its own reality and the world around us is a tremendous privilege. And I would just suggest that people take more advantage of that in whichever way they see fit. I'm not saying that physics is the only way to study science. There are so many ways to study science, and there's so many different sciences. And so I think that just I would encourage people to pursue active thought and the idea of constructive collaboration with others, and just enjoy the ability again to perceive and think about the world around us in extreme depth as our minds allow it. I think that's a very exciting time to be alive. So definitely engage in science. Definitely engage in science communication and spreading correct information and excitement about science.
This really was a conversation at all the different aspects of the bleeding edge of science, computation, and a little bit of sprinkle of philosophy. I really appreciate how you were kind enough to really go through with all these different concepts and topics that I was curious to talk to you about. So, really appreciate it. Thank you. Thank you so very much.
Yeah, thank you very much. I really appreciate the opportunity, and this was a lot of fun. Yeah,
Thank you.